Hello everyone, my name is Juan Cadile and I'm a dual major in computer science and philosophy. I'll be presenting my my thesis called The Wire Machine Computing Causation. I would like to first thank Dr. Berry for not only all his support, but also for being my first philosophy professor, my first semester here at Iona, and thank you everyone for listening to my upcoming monologue. So for today's presentation, I have only three goals. Firstly, to show that philosophical issues about causation entail real and practical consequences that extend from daily life to big scientific questions. Secondly, to explain in simple and clear terms how state-of-the-art cause models work and show their limitations. And finally, to entertain the idea of building a machine that can answer why type of questions, that is, questions about causes and their effects. There's a huge philosophical struggle regarding the nature of causation. My thesis does not try to answer such questions. I start with the assumption that causes are real, that is, that the world has a causal structure, and based on that, I try to answer the following. What tools, models, and information are needed in order to build a machine that is able to answer a certain type of questions about causal relationships? We all have heard that correlation does not imply causation. But it seems like correlation is all that we can observe. In other words, all we have are observations of correlations, and then our minds make the extra work of generalizing. For example, given that cause precedes effect, and we see things happening one after the other in a seemingly continuous way, we infer from those observations that there is a causal structure behind the occurrence, but we don't get to see the causal structure, just some of its correlations between inputs and outputs. So, if we cannot observe the causal structures that cause things to happen, rather than only observe correlations, the question becomes, can we infer causation from correlation alone? The answer I entertain is that correlation alone won't do it, but it is a useful starting point. With this first example, I just want to show you that causality is not just an academic issue. This example shows that causal questions are evidently practical. This example particularly would help determine whether any of us should buy a red car. The correlation given is that it is known that red cars correlate with higher insurance rates. What we want to do is determine if there's a common cause to the correlation we observe, and if so, we want to determine what the cause is. So let's run through three possible scenarios and their consequences. Cause 1 says that the color red attracts the human eye more than other colors. That is what causes the police to notice red cars more than others, which leads to increased tickets and therefore higher insurance rates. If this is true, then we probably should not buy a red car. Cause 2 says that the color red makes humans drive more carelessly. Unless this can be proven, say by neuroscientists, it is probably a false correlation of color with bad behavior, meaning we should probably discard these claims because we are the cause of our own behavior, not the color of the car we drive. Cause 3 says that people that drive carelessly tend to buy red cars more than other colored cars and more than safe driving people. Therefore, if I am not a careless driver, I may just buy a red car without worrying much. Hopefully this example shows the practical implications of causal questions that cannot be answered solely with statistical correlation talk. This is yet another example of why just association or correlation is not enough. We at least need to know how to interpret data. But if we are to build a machine, we're in big problems. It seems like the only beings with high cognitive functions can make such inferences, meaning only to a human the conclusion exercise is helpful in every age group but harmful for a typical person sounds incorrect. How do we ingrain this into a machine? There are no mathematics or any logic in existence that can explain why statistic averaging arrives to this error conclusion. So we need to formalize our mental model that tells us there's something wrong in the way the data was interpreted. This means, without formalizing our mental model, the machine cannot answer correctly the question, given this data set, is exercise helpful in reducing cholesterol or not? The illustration shows what is known as Pearl causal ladder. These three levels, association, intervention, and counterfactuals, are mental models that we humans have that are useful for talking about causality. Both previous slides have made it evident that we cannot answer causal questions if all we have are associations. We also need levels 2 and 3 if we want to make these inferences. That is, jumping to conclusions that are not explicitly there in the data. We also need to be able to interpret such conclusions to hopefully know whether we went wrong along the way, like in the previous slide example, and think about other possible cases, meaning cases in which variables take the different values. In my thesis, I also explore examples whose conclusions cannot be known to be correct or incorrect. For example, questions that would involve a complex model of the whole universe. But overall, what we need is language for levels 2 and 3. It seems that math and statistics only provide language for level 1, and then we humans can make interventions given level 2 and imagine counterfactual scenarios given level 3. Together, these mental models lead us to causal answers, but there is no formal language or logic for it. There is no tool other than our mental models. In other words, to summarize the whole slide, the causal model is in your mind. You cannot smuggle causal theories into data nor code them. Therefore, a machine cannot do any of these interpretations. Only we can. So the goal then becomes to give a machine the capacity to understand causal relations. That is, to be able to model, compute, and make inferences. In other words, we need to find ways to download our mental causal models into a formal language so that computers can compute with them. Some related issues that arise with this are, firstly, where does the knowledge reside? Do models contain knowledge? Or do models provide enough for making inferences? This means, do we imbue causal models with knowledge, or is it still in the scientist that is working the computer and is interpreting the data? Another important question that is super important in unobservable environments is, can we, and if so, how do we discover unobserved causal relationships, which is also known as prediction and retrodiction. Example of prediction, what would happen to Y if its parents take certain values? An example of retrodiction, what would have happened to Y had their parents taken different values or were partially absent in the model. This is a very technical slide, so I'll try to summarize key points, and those interested may also read. I just mentioned in the previous slide that we need to formalize causal calculus in order to make machines that can speak and compute in causal terms. Pearl claims that the main issue is that mathematics does not suffice to talk about causation formally. That is, he says, because the equality sign does not work in causal settings. In plain English, the cause does not equal the consequence, and therefore the equality sign is not useful for our purposes. He proposes utilizing arrows instead of equality signs and to use directed acyclic graphs as a great tool to model causal relationships in a visual way. He also creates something called the do operator that forces a variable to take a certain value. For those wondering what a directed acyclic graph is, here you have an example with graph G. In graph G, the wetness of the ground listens to the sprinkler and the rain, and both the rain and the sprinkler listen to climate. An issue here is, where do we put a boundary to the domain included in the model? Meaning, we could probably think of more causes of wetness, but do they matter to the question? Should we include all possible causes if they don't matter to our question? The graph G, along with the model M, are non-parametric in that they don't show the full function of each variable and how it responds to specific values taken by the parents, but it still lets us know a bunch of information. For example, we can at least, knowing that the climate is sunny, know that the only possible reason in this model that the grass is wet today is because of the sprinkler. So we can start to make some type of deductive inferences. One of Pearl's main contributions is the do operator to analyze counterfactual scenarios. When we analyze a do operator, like do sprinkler on, which we can physically do on turn the sprinkler on, it eliminates the arrow that determines it, as we are forcing a value. That is called blocking backdoor paths. With this, the manipulated model, we can see that we can see what the child variables, the values that they take. For example, we do sprinkler on, and then the surface is wet. Some problems associated with the model are, firstly, the reality of the interventions. We can turn a sprinkler on, but there are so many things that we want answers to that we cannot physically, logically, or metaphorically do. Secondly, it seems like we may have not imbued enough information for a model-based machine to make inferences on its own, nor for a machine to generate graphs only from data. A possible workaround is to have a big collection of graphs with their corresponding data, and then find a way to match such data and graphs. Lastly, we have the issue of completeness, which is not unique to this model, but to all variable-based models. Finally, let's talk really briefly about what it takes to build a Y machine, and why we would want anything like this. Are the models that I presented enough, and what are some challenges? The main reason for creating such a machine would be to create a tool that would aid scientific research, but this would just be the beginning. In my thesis, I argue that if we are to make such a machine, causal models are not enough. Necessary, but not sufficient. We need many other features, such as a world model, inference-making functions, causal models, plus metadata about the background assumptions of each model's application, intercommunication with other AIs to share graphs and error correction, and models for dynamic systems, given that not all causal relations are acyclic. The biggest issue, aside from creating a world model, which we don't know how to do, and it would probably exhaust our current computational capabilities, is that we really have no clue on how to formalize an inference-making process. I argue that on the very minimum, we need metadata about the causal model and some type of supervised training. That is it. Thank you everyone for listening.
So one of the challenges you mentioned was that you didn't have enough data to have a world model. What if you were to make like a smaller, like kind of almost microcosm of it? Like you don't have to make it obviously the whole world, but why not, let's say, a state or something like that?
I think this is a micro model, for example. We can make things like this. I've been thinking a lot about making a world model, and I think, and this is where it gets weird, if we ever have human-machine interfaces, that is something that we could probably do. But how do we get all variables into a model? That would be the big issue. And do they matter? And then do we have redundant variables? Do we have conflicting variables? That's where it gets really messy.
Gimmicks on my bed. Oh, okay. The question I have is seeing the outside of this, how does this compare to, say, like IBM Big Blue for making those types of decisions?
I don't know how Big Blue works, but most of machine learning is just matching patterns and curve fitting. They don't have any type of directed graphs, and all of that is based on math. So we have the issue that we have an equality sign, which is not appropriate for causes.
Okay. Thank you.
Yeah.
I was just going to comment. We can go back to that ladder. You said there's no mechanism for modeling the what-if scenarios.
There is no, well, now we have for counterfactuals with this, right? But with plain statistical models.
Looking to branching time temporal logic.
Okay. I didn't know.
Sounds like that's perfectly suited for that kind of modeling.
Perfect. I didn't know that. But basically, what we see with just statistics is level 1, and what we see with what I presented today is that we get a really basic notion of intervention and counterfactuals given such model that you see model M and graph G. But I would love to see how that works and maybe they can be integrated. Yeah, thank you. Any questions? Yeah, Mike.
I'm sorry, I'm going to be
No, okay.
So you mentioned, as you mentioned that most AIs already work off pattern recognition.
Yeah.
So wouldn't it be possible to at least have it make inferences based on certain patterns? Like obviously certain weather conditions, there's a pattern where there's a more likely chance for it to rain. So wouldn't you be able to train it to help predict whether or not it's going to rain? Or
This is a different, those are different questions, I think. Predicting, is it going to rain, is a different question than why is the grass wet?
Okay.
Or why is it rare? The very different questions. Any others?
Thank you.
Thank you.